Okay, Unit 3, Part 3 is on the Kinetic Molecular Theory and gas laws. So here are the 5 points of the theory. If we just, I'll let you read through these. We know gases are always in motion. And what we're assuming here, and this is for an ideal gas, that all the molecules of the gas really aren't taking up space in the container. That's really what number 2 is saying. So that's an assumption we're making. And then, again, this is for an ideal gas, and we'll talk about real gases later. But we're assuming that the attractive and repulsive forces between gases isn't happening, and that all of the energy that's transferred is transferred between molecules during collisions. And you might see that collision called elastic. And then we've mentioned this earlier, but average kinetic energy is proportional to absolute temperature. Okay, so real gases versus ideal gases. So as I said, ideal gases are described by the kinetic molecular theory, and we'll look at PV equals nRT later. But what we do know that real gases do take up space in the container, and if the particles are forced to be close enough together, they could be affected by attractive forces, which is where IMFs might come into play. Wow, that's very messy. So what I mean are IMFs, the attractive forces. So at high temperature and low pressure, real gases can behave most like ideal gases. So why these two scenarios? And you do need to know those two. So what is it about high temperature? Well, if you think about it, at high temperature, that indicates high average kinetic energy, which means the gas molecules are moving around really fast. If they're moving around really fast, what's not going to be affected is if they're polar, maybe molecules, they're going to have so much energy, those attractive forces aren't going to be important. And if you think about low pressure, and we'll talk about Boole's law later, low pressure refers to a high volume, or a large volume might be a better way to say it. So if there's a large volume, the space the gas particles are taking up in a large volume is going to be very insignificant. So again, I've kind of written all that out, so maybe that would help you understand it better. So another question is, what kind of gas would deviate most from ideal behavior? Well, we'd want, if you're trying to figure out what gas would deviate most, you'd probably want a polar molecule or a gas under really high pressure. Because if it's high pressure, you have a very small volume, and the particles would take up some of that space, and it would matter. So let's look at some gas laws. If you'll notice on the formula sheet, there are very few gas laws listed. There is PV equals nRT and Dalton's law, which we'll talk about as well. And I'll kind of show you how we can derive or see these other laws, because you really do need to know. But first, let's talk about pressure. Pressure is the result of gas particles striking the sides of a container or your skin or whatever, okay? So the more particles you have hitting the container, the more pressure there would be, okay? If we decrease the volume, there's going to be more pressure. And whose law is that? Well, that's Boole's law. We don't need to know these specific names of the laws. You do need to know the relationship. So this is an inverse relationship with Boyle's law. And then if we have faster particles, again, what would cause gas particles to be moving at a fast rate? It would be a high temperature that have high kinetic energy. That also would be more pressure. So here is Charles's law. Again, the names aren't really important right now. It's knowing the relationship. So since it's V1 over T1, they're going to increase and decrease together. So this is a direct relationship. And most gas laws are direct. It's Boyle's law that's inverse. Other gas laws that I know you've probably used in your first year class are the combined gas law, and then Avogadro's law is in this box. Avogadro's law deals with, and you could also write it like this. volume in moles. If we have a flexible container, and it's just like blowing up a balloon. The more moles of air that I blow into the balloon, the larger the volume gets. So again, any of these that are divided like that are going to be direct relationships. So just as I said, don't worry about these individual gas law names. And one that's not mentioned here is Gay-Lussac's. It was P over T. So again, any of these we can see and find, and we still need to know all these relationships from the ideal gas law. Okay, so just let's go through the details of the ideal gas law, and then I'll show you what I mean, how you can find all these other laws from it. First of all, really important that you watch your units. The R on the formula sheet, there are 3 versions of that. It reminds you of what units you need to have. So if you're given a pressure, the pressure you're given, whatever units that's in, that's going to govern which R you use on the formula sheet. Most commonly, maybe we'll have atmospheres. We could have millimeters of mercury. Again, make sure you've looked at that formula sheet. And with volume, a lot of times we're measuring volumes in the lab in milliliters. This volume always has to be in liters. So this is going to have to be in liters. We know moles is in moles. And as we see here, in any of these gas laws, temperature has to be in Kelvin. Okay, Celsius would have a negative temperature. We're always going to add 273, that's on the formula sheet, to get a Kelvin temperature. So a couple of these, no matter, it's really the pressure that's changing, the pressure units are changing the value of our volume has to be in liters, and temperature definitely has to be in Kelvin. So how can we see these other gas laws from PV equals nRT? So let's erase these. I'm going to erase this, and I'll just kind of make it a little cleaner, and I want to show you. Okay, so we know Boyle's law is P1V1. If I look here, see if whatever's changing in these individual gas laws, everything else that's not in the individual gas laws is held constant. So Boyle's law is just P times V. Okay? Moles and temperature are constant. All right, so then if I rearrange this, okay, I can say P times V. I'm going to divide temperature to the other side equals N times R. Well, that looks like the combined gas law, doesn't it? So if the moles are constant, it's PV over T. That's the combined gas law. I really can see I can see Charles's law, and I can see Gay-Lussac's from this relationship as well, because if it's Charles's law, it's just V over T, I'm trying to circle that, which means pressure would be constant. All right? If I was looking at Gay-Lussac's, then it's pressure over temperature, and volume in moles is constant. Okay, so again, you can see all these individual gas laws. And the last one is Avogadro's law. And basically all I would do is I'd divide pressure to the other side, because it would be constant, and I would divide moles to this side. So V over N, again, all I'm doing to find all these gas laws is rearranging the ideal gas law. In addition to seeing the individual gas laws in PV equals nRT, we can also rearrange the ideal gas law if we're asked about molar mass of a gas, or, possibly given its density. So you don't really need to be able to derive this. This is used, occasionally. It's not that common. And so you can see how that's been rearranged to get density. Because remember, density is grams per liter. That's where they're getting the density, is the mass over volume. So another way, just because this is not on the formula sheet either, it's just kind of a specialized version of PV equals nRT. I was given the mnemonic device that, if you just kind of do the abbreviation, as you see I've highlighted, molar mass cat, because you think of those memes. Molar mass cat puts dirt, DRT, over its P. So anyway, that might be the one way to remember that if you ever need it. We have said that gases, we have a temperature that is proportional to their average kinetic energy. There is a formula on the formula sheet that deals with kinetic energy, and it looks like this. And really this is just a relationship. That's a lowercase v for velocity. So it's Ke, kinetic energy, equals 1/2 mass times velocity squared. And this is where the second statement's coming from. Atoms or molecules with smaller masses have to move faster to achieve the same kinetic energy as larger mass atoms or molecules. So in other words, even though multiple gases are at the same temperature and they do have the same kinetic energy, that does not mean they're moving at the same speed or velocity. The speed or velocity that they're moving is at which they're moving is based on their mass. So if there's a low mass atom or molecule, it's going to be moving faster at the same temperature than a heavier, more massive atom or molecule. And I put this in bold to because this is an easy way to be kind of led astray on a multiple choice question. If the temperature is not changed, no matter what else is listed in the problem, the average kinetic energy of a gas doesn't change. So if you're told the temperature is constant, think in your mind when you see that that means average kinetic energy is the same for all gases. And here's the Maxwell-Boltzmann distribution. This is a very common graph. Higher temperature means faster molecules. And I kind of showed you another version of this in a previous I think the part 2 PowerPoint, where we only had 2 lines on that. Notice usually temperatures aren't given. You're supposed to be able to estimate a temperature by taking, going to the top of the curve, and if you draw a line straight down, you see that this is the average speed of these different molecules. And so we can see that the higher temperature, which is the 1000 Kelvin, definitely those particles are going to have the highest average speed. So what does a distribution look like for different noble gases at the same temperature? So if you think about it, this is 4 different temperatures. What if we had one temperature but 4 noble gases? Would they all have the same speed if their temperatures are the same? So would it be 4 overlapping curves? And hopefully you're thinking no, because what's different about the noble gases, and here are the 4 that they've chosen: helium, neon, argon, and xenon. You see that those 4 noble gases, and those are their molar masses that are listed, have extremely different masses. So the one that, even though the temperature is the same, it's helium that has the highest average speed because it has the lowest mass. So this is where the mass comes into play. All right, so partial pressures. This is where we kind of start getting into and working towards Dalton's law, which is on the formula sheet. There is another relationship I want to make sure you understand before we get there. A mixture of gases in the air around us is responsible for total pressure we call air pressure. Okay, we measure this with a barometer. We might call it atmospheric pressure. So, but we can figure out the partial pressure of each individual gas. So let me just give you this scenario. If we have 20 molecules of gas A and 40 molecules of gas B, and the mixture has a total pressure of 30, what is gas A's partial pressure? See, what we need to know here is, how much is gas A taking up of that total mixture? Okay, so notice how I set this up. Well, the answer is 10. Let's see how I got 10. So if we're talking about A, there are 20 molecules of A out of, what's the total number of molecules in the mixture? Well, it's 60. So 20 out of 60 is 1/3. So what's 1/3 of the total pressure? It's only 10. Okay. Now gas B would have to be the remaining 20 millimeters of mercury of pressure, but let's calculate it, and so you can see hopefully how I'm getting this. So B is 40 molecules out of the total of 60, which is 2/3. What's 2/3 of 30? It's 20. Where is this relationship coming from? Well, this, I just took a snip of what it looks like on the formula sheet. Okay, really when we take 20 of A over 60 or 40 of B over 60, we're doing this mole fraction. Okay, so when you take this mole fraction, like for A, we had it was 1/3. What's 1/3? Here's our, this is called chi. It's just a mole fraction. It's really what it means. What is the mole fraction times the total pressure? And so that's what we did. We said 1/3 times 30 and gave us 10. Or for B, we said 2/3 times 30 gave us 20. So this relationship is on the formula sheet. Just wanted to go over that so that you could just maybe understand this example without even needing this formula. But I do want, if you see the formula on the formula sheet, I do want you to understand where that's coming from. So remember this chi is mole fraction. All right, here's Dalton's law. Again, we're talking about individual gas pressures. So in a mixture, we call those individual pressures partial pressures. And this is probably the easiest formula. We just add up the individual partial pressures of gases, and that's what gives us the total. Now, and we'll talk about this more, a little bit more when we get into Unit 4, because that's where stoichiometry comes up. But just since we're talking about gases, in the lab, if we're going through a reaction and we're collecting a gaseous product, we have to collect that gas over water. Okay, so basically you'd have some kind of tubing. I'll show you a picture on the next page, or a gas collecting tube. There's lots of ways to do this, but basically the gas that's being collected would bubble into another container, like an inverted graduated cylinder or a gas collecting tube that's filled with water, and displace the water. Okay, so the gas that's being collected would contain some water vapor depending on the temperature. Okay, so this is going to be another example of Dalton's law of partial pressures. And why would collecting a gas over water contain water vapor? Well, it's what we said when we talked about liquids. All liquids contain some of their vapor above their surface. If it's a high temperature, there's going to be more vapor present. If it's lower temperature, there's going to be less vapor. So let's continue with this discussion on this slide. And you can see here they're decomposing. It's a decomposition reaction with potassium chlorate. Oxygen gas is a product. It is forced to go through this tubing. This jar was previously full of water, and when the oxygen gas bubbles into the jar, it pushes the water out. So that's what I mean about collecting a gas over water. So again, if this is a graduated container, we would know the volume of the gas we collected. So when a gas is collected over water, the gas that's being collected also contains some water vapor. So again, it's just a repeat of what was on the previous slide. So here's how this is Dalton's law. We would be told the atmospheric pressure, like the barometric pressure reading. Now, the pressure of the gas we're collecting, in this case it would be the oxygen gas, is the sum, the atmospheric pressure is the sum of the pressure of the gas we're collecting plus the water vapor pressure. Okay, this water vapor pressure at whatever temperature this experiment is taking place at should be given in the problem. Okay, so really what we need to do here, because this is given and this is given, is we just need to rearrange, and we can actually figure out the pressure of the gas we're collecting by just subtracting the atmospheric pressure, which came from our barometer, minus the water vapor pressure, which really is a table in the back of a book that's designated at different temperatures. Okay, So really it's a really simple subtraction. You just have to know to do it. And that ends the gas discussion.